Hello, today we're going to talk about working with systems of two linear equations and two variables. All right, the first thing we're going to go over is the different type of solutions you get from systems. So the first one is just what you usually end up getting, and that's one solution. One solution graphically looks like this. It's where your two linear equations cross each other. That's the point, that is the answer for it. Algebraically, you'll get something like y equals 3x minus 5 and y equals negative 2x plus 4. All right, something along those lines. Their slopes are different. Their y-intercepts can be the same, but their slopes are different. What's important here? All right, when their slopes are different, you're all good. All right, it's going to be a one solution. Yeah. All right, the next one you need to know is no solution. So no solution graphically will look like two lines going on forever and ever in the same direction. All right, they're not crossed. These are called parallel lines. All right, graphically, it'll look like this. All right. What is different between this and this? Well, they have the same exact slope. If they have the same exact slope and different y-intercepts, that means they'll keep growing at the same rate, but since they have different y-intercepts, that means they will never touch. All right, so if you ever see them with the same slope but different y-intercepts, it's going to be a no solution. The other way you could see this is if you had something like negative 5x plus 2y equals 8, negative 8, and negative 5x plus 2y equals 8. All right, you know when you move the 5x over for this one, and when you put it in slope-intercept form to find the slope, since these are the same and these are the same, you know your slope's going to be the same. But since that's negative and that's positive, you have a different y-intercept. All right, if you want to go through and do it, you can, but that's just another way to look at it. All right. And our last one is infinite solutions. All right, when you have infinite solutions, that means they're the same exact line. It's usually drawn like this, but with different colors. So it's just a line that overlaps a line. Another word for this is coincide. They coincide, they're right on top of each other, they're the same thing. Examples of this are y equals 2x plus 1 and y equals 2x plus 1. Same exact equations, so there's infinite solutions between them. Another way you might see this is y equals 3x minus 6 and y equals 3x minus 2. All right, those are still the same equations. One is just distributed, or this one's simplified. So if you distribute the 3 in, you get the same equation. So those are the three different types you will see. One solution, no solution, and infinite solution. All right, here's an example. So just by looking at it, I can kind of guess that it's going to have a solution, just because I've done this a lot. But we need to put them in slope-intercept form before we can, well, it's a system. We'll just do it a system way. I like doing substitution, but this is set up for, we'll do something fancy. We'll do elimination, all right? How I do this is I do substitution, so I solve both for y and equal them to each other. But we'll do elimination, why not? So I'll multiply the top, everything by 2. Now there's a lot of different ways to do this. This is just the way I like to do it. And now I have my opposite. I have negative 2 and positive 2y. And that's 14. So now I add these together. I get 5x, that equals 0, equals 30. Divide by 5, divide by 5, x equals 6. Now I take that 6 and I plug it back in for one of the equations. I'll do this one. So 6 minus 2y equals 16. So your answer is 6, negative 5. And that's how you solve. All right, for our next example, it's a word problem. All right, I'm gonna show you how I do word problems. There's another way in this and in the next lesson that shows you how to do them. This is just how I prefer to do it. So there are 200, when I know I'm doing systems, all right, I like to set it up. So I say X, Y, and a total, all right? And I know I'm gonna need 2 of these, so I'll call this 1 and 2. Because it's systems, you know you need 2 equations. Now, if I need to switch it, if I see it's something else, I can do Y, or I can switch it up, but this just gives me basically what I need. Most of these you're gonna see are the tickets or buses and vans example. Another one is the chickens and pigs problem, or chickens and cows problem. But this is how I set it up. So it says there are 220 tickets to a school's annual awards banquet. So that's one of my totals, is 220. All right, this is how I set it up every time. If you wanna make a little chart out of it, you're more than welcome to. So that's my first piece of information. Check, I've used it. Don't need to go back. Adult tickets, A. So I'm gonna switch my X to an A as I'm going. You can leave it as X if you want, but just for this example and the question, how it's asked, I'm gonna switch it. I usually leave it as X. Costs $25. Oops. I'm not gonna use that yet, and student tickets cost $15. All right, so I know this information and this information. So every ticket sold, and they made a total of 4,650. I like to find my totals first. So this is dealing with money, and this is dealing with people. All right. So what type of people went to this? So a total of 200 people went because it says it sold every ticket. So if I just add my adults plus my students, it's gonna be 220 in the end. I don't have to switch anything else. Now the trick is the money. So I have adults plus my students, but for every student ticket, how much did it cost? It cost $15. For every adult ticket, how much did it cost? Well, $25. And there you go. There's your 2 equations. So A plus S equals 220, and then 25A plus 15S equals $4,650. That's your system of equations that you need to get out of this. And then you can solve it however you want. I would do substitution. I'd solve for S. So I'd move the A over, substitute that in, solve, and so on and so forth. But that is basically what you'll get. So the good thing about knowing that it's a systems problem is you know you're finding 2 equations. What format they're in, they're usually in this, but every once in a while you'll get one that looks like this. And that's usually when you're comparing 2 things, like plumbers or car rental agencies, something like that. So that's how you do this one. That's your answer. All right, here's our last one. Word problem. So Jill bought 8 packages of markers. So again, I know I'm trying to come up with a system, so I know I have 2 equations, an X, a Y, and a total. Put them closer to each other. So Jill, I can call it, put Jill if I want here, bought 8 packages of markers, and they wanted to label as M, and 4 erasers, W. And that cost $72. So this, and that are all informations. Got my total in, I got how many markers and how many erasers. Jack bought 12 packages of markers 2 erasers for $98. What is the cost of the marker package? One marker package and one eraser. So I have basically everything I need. I just need to put my variables in. So write this a little bit clearer. 8m plus 4w equals 72. 12m plus 2w equals 98. Now this is set up for elimination, so that's what I'm going to do. Alright, I'm going to switch this to a -4, so I'm going to multiply this whole thing by -2. Gives me negative 24m minus 4w. Just to make sure I don't do anything wrong. Negative 196. I'm going to bring my top equation down. And there we go. Eliminate. Negative 16m equals, again, you don't want to mess anything up, which you probably will anyways. Alright, so M equals $7.75. So one package of markers is $7.75. So I plug that back in, and I can figure out what my W is now. If I want to know how much my erasers are, which isn't cool, but 7.75 plus 4W equals 72. I'm not going to take you through all of it. I'm just going to cut here and then go to. So an eraser costs $2.50. So markers are $7.75, a package of them. Erasers $2.50. All right, this has been working with systems with 2 linear equations and 2 variables, basically word problems.